Okay, so it's really fun to be here. And I pointed out to Andrew this emblem at the right. This one. Do I have a pointer or what? This one.
Yeah.
This is KITP, which few of us met here, Kater, Alexia, Andrew. And the point is, you have to meet people. This is so that's why I'm happy to be here, because if you don't meet people, you don't talk about what you do, you get nowhere. So now it was 4 years, and now we're again trying to meet people again. So this is why I think this is an important event. What happened here? Tells me it's recorded. I got it. I agreed to everything. Okay, so what I want to tell you is a slightly different subject that we heard before, but we'll see their connections to what we heard now. And it's, you could say the story I want to tell you is about quantum control, and you can stop me in the middle. That's always good. So let's see how this goes. Wait, just move like that. Didn't move here.
I think you have to go full screen.
I am full screen.
Give it a second. Sometimes there's a delay.
It doesn't move here. The zoom.
Maybe stop sharing your screen and start sharing your screen again.
Oh, there it is. There it is.
Yeah, but they do. The full screen. Work. There's a problem. It's frozen. You know. Stop share. Let's share again.
It's the green button.
Green? I don't see it.
Scroll down to the.
There is conflict between Zoom and this, but if it's solved, that's good. Okay, so hopefully it works. Okay, here are people involved. So some you know, some people know them. So Roidan was at Santa Barbara. He just graduated. So a lot of the work I'm going to talk about, and Kater knows him not because of his work, because he went surfing. And Shimshon Kalush is a long collaborator of mine. Aviva Roch is a graduate student, works on control. Amikam Levy was also at Santa Barbara, but he was at early stages of this. And earlier people that I worked on control is David Tanner. Alon Bartana was a graduate student of mine, which we worked on open systems. And there was also in Santa Barbara, and we collaborated on part of the work. And Christiana Koch, which I think Alexia knows. So these are the people who were involved. And so let's see what I want to tell you. Here. So what we want to do is quantum open system control. So what you need for control, and unlike what Alexia talked, my driving field is going to be classical. So you could say what you have here, you have a Hamiltonian, which is the drift part in the controller, and you have an operator that's used for control. And the equations of motion that we're going to use is the revealed von Neumann equation. So this is what we have to get. And in general, we know H generates the unitary dynamics, the dissipator is the dissipative dynamics. And in control theory, there are two types of things that we can think about. One is state to state. I want to go from an initial state to final state. And one is process control. I want to get a gate. I want to go from an initial state to a final state, but what I'm interested in is the gate itself, which is independent of the input. So this is the algorithm. The algorithm is independent of our input. So these are the general settings of control. I have to get the right setting. So how does control work? So control is an interference, quantum control is an interference phenomena. And what we want to do, if I want to go from an initial to a final state, this is my objective. I want constructive interference here and destructive interference here. So the agent, what I need to generate quantum control, I need coherence. Without coherence, quantum control can't work. So you can see already this is the conflict that we'll have this open system that we degrade our coherence. This we saw. Somehow I'm pressing the wrong button. Okay. So now there's an issue, which is a mathematical problem. Control theory in general is an engineering field. It's well established. And you could ask a few questions, and this is controllability. Giving a setup, is it controllable at all? Is there a solution to the control problem? And this is something that has been dwelt on since, you can say, in the 30s in the mathematical control theory, and was introduced to quantum mechanics in this paper, 1983, by, you could say, these are two control people and a physicist. So the question is, okay, given a Hamiltonian, which I have a drift Hamiltonian and an operator, what are the conditions for the control operator to get complete controllability? And when you say complete controllability in this setup, it's complete unitary controllability. It means I can generate any unitary operator. And the theorem is based on Lie algebra. It means that if you take the commutation of V with the drift Hamiltonian, you take all the commutators that are generated from that. If you get the trivial algebra, which is called UN, then it's completely controllable. So it's a statement about commutators.
And your epsilon is you shape it the way you want.
Okay, so and this is mathematics. So epsilon is free.
Yeah.
So you're asking, okay, if I can do anything,
yeah,
on epsilon,
yeah,
what are the conditions on V to be completely controlled, okay, on the operator?
Okay.
Now, typically you put constraints, additional constraints on the field. You say it can be too strong, it has a bandwidth, or so. This will reduce your controllability, but this is a statement. Now, unitary dynamics preserves entropy. So this already means that if we want to extend it to open quantum systems, this control theorem is not good enough, because if we want to change the entropy of our system, this theorem wouldn't cover that. And so in order to get a general control in open system, that we need a dissipator. Without the dissipator, we can't get complete controllability. And then we will ask, can we control a gate? And I'll get to that. And the final point that I want to stress, that the question is the dissipator independent of the control Hamiltonian. And what I'll show you that they are linked. Okay, so what I'm interested in is an entropy changing control tasks. That's why we need open systems. So as I said, it can't be done in a closed cycle. And there are different types of control tasks we can think about. One is what's called fast equilibration. And this is called Mapemba effect. You know what Mapemba effect is? Okay, I'll tell you a side story. Mapemba was a popsicle seller in Tanzania. And this is his name. And he wanted to sell popsicles at the beach in Tanzania. And he found out that if he starts with hot water and puts it into the freezer, he gets the popsicles faster. So this is called Mpemba effect. First of all, there was an argument if this is correct or not. I did an experiment with my grandson, taking liquid nitrogen from the lab, bringing it to my kitchen, and we tried it. It's correct. The effect is verified by my grandson. So he's
Certified.
so the question, how does this work? I'll go back to that in a minute. There is quite a lot of literature. The truth is about water, nobody knows, but in other systems, we know how this works. And then you can say laser cooling is a general scheme that we want to control and do it fast. And optical pumping, these are all entropy changing operations. So if we want to optimize that. And then a reset, this is Landau eraser is another example. Quantum annealing, if we want to schedule a D-wave computer. And here I have non-unitary gates, but we can also think about unitary gates and now use them. So these are tasks that we want to do. So now we need a framework. And the framework that we need open system dynamics. And you can say this is the issue, the agent of control coherence is degraded. So we're playing in a game. We can't dissipate too much because we'll lose our agent of control, but we can't be unitary. Okay, so now we're moving to quantum thermodynamics, and we start from quantum mechanics and we derive, you can see, the laws of thermodynamics and build a consistent theory. This is what I want to stress here. We want to build a consistent theory that we later can use for our quantum control. So these are the theory that we want to get. And here, I think Alexia started with the same. This, you could say Hamiltonian of the universe. I have a system, environment, and coupling. And I'm going through, you could say, the basic ideas of what's called a reduced description. So we assume that the total universe is unitary and generated by, you can say, this unitary operator. But the reduced description has a reduced map, which we can write it like that. And if we can write it in a differential form, if we can write it like that and it's an exponential, we have a master equation. So we have an equation of motion for a reduced description. And if we want control, we have to have an equation of motion. We can't do control without that. So this is what we have to do. So our first target is to derive the master equation. Okay, so what we want is a thermodynamic consistent master equation, because you can say in general a master equation can be correct or not. So at least we want something that is thermodynamic consistent. And the point here that there's the unitary part and the dissipated part are linked. So how do we get that? Okay, so this is, if I'm going too fast, just tell me. I'm reviewing the general theory of open quantum systems. So it starts with Krauss, which says the completely positive map has this structure with this element, and building on you could say on Krauss, Lindblad and Gurini, Kusakovsky, and Sudarshan developed this equation, which is you could say a master equation, which is Markovian dynamics under strict energy conservation. And there are two assumptions. First of all, it's Markovian, and then at some time, the system and bath were uncorrelated. So it's mathematical. This is mathematical physics. It's extremely useful because you can guess. So you don't have to derive. If you have the structure, at least you know you obey these conditions. So we're going to kind of, in a way, continue this idea of, you can say, axiomatic approach, but you can show that this is not sufficient for the thermodynamics. And There are many examples. You can show most elementary thing that heat can go from cold to hot, and I can write a master equation like that. So we don't want to do that. We want a master equation that's consistent with thermodynamics. We have to add conditions to that. And these are the conditions. So this is called thermodynamic restrictions. And let's say the first thing, the map is Markovian, satisfying the semi-group property. We can relax that, but I'm not going to talk about that. The environment is large and remains stationary. So it's not like your environments that could change. In my case, in one condition you have that. In my case, my environment is always big and stationary. The fixed point is a thermal state with the temperature of the environment. And here, number 4 is what Alexia taught us, that the interaction commutes with the system and energy. So this is sometimes called strict energy conservation. Here is a paper that we published about what does this mean. So I'll summarize that. So this is, now we want a master equation that has that. So, I went the other way. Here. So physically, what does it mean? Here's my system, here's the environment, and here's my interaction. So strict energy conservation thermodynamically would be called isothermal partition. Energy flows from one side to another, but doesn't accumulate on the interface. So in the thermodynamic limit, the interface goes away. So thermodynamically, it's correct. But we want to go to quantum mechanics. So Alexa showed us how you can go to a small system, and this will still be correct. So this is this condition. Now, if you take this condition and you look at the free propagator and the dynamical map, they have to commute. So we get this condition that you can say the generator of the unitary part and the generator of the dissipative part have to commute. So this is a condition on Liouville space, on super operators, on this commutation. And once you see something like that, you see a symmetry. There is a symmetry involved here. And I put Emmy Noether as the, you can say, the mother of these ideas. And so we have a dynamical symmetry here. And you can think, what does it mean? It means, in a way, that the free propagator and dynamical map commute, that the bath can't serve as a clock. So there's translation, because free dynamics is time translation. So if I can move my system and contact to the bath now or later, the response will be the same. So this is, now if I look out, the environment can be very good clock because I see the sun, but that's not what's working here. So this is a dynamical symmetry. So we know if two operators commute, they have eigenoperators. So they have a set of eigenoperators, not eigenvalues, but they have a common set of eigenoperators. So we can show that in this case, the operators here that appear in the Lindblad equation are eigenoperators of the free dynamic. So we don't have freedom. We lost the freedom to take the dissipative part and the unitary part independently. There is a close connection. They have a common set of eigenoperators, and you can see the dissipative part has to look like that.
And what is the rationale of imposing these conditions?
Strict energy conservation.
Okay, you want
It's a
strict
proof.
energy conservation.
It's a
Okay.
proof. Once you say strict energy conservation, the maps,
Okay.
the way to prove it, this is a differential form. You prove it on the map. So dynamical map, the unitary dynamical map and the dissipative dynamical map, the way you prove it, the total map commutes.
Yeah.
With the,
So it's a measuring apparatus. Okay. For the energy of the system.
Is that, I understand if that's a restrictive assumption or not? Like, does that mean that my normal qubit Hamiltonian undergoing spontaneous emission violates this, or is this?
it could, In many cases, yes.
Okay, because oftentimes my dissipator is something that doesn't compute with. my
If you
system,
just
or-
take it out of the wall, it will vibrate. So it doesn't mean it's not, doesn't work for your setup, but if you look,
But this is like, yes, but this could. easily be
if you want to be consistent with thermodynamics and you take this is what you get as your equation. Okay, here. Okay, so we did it for time independent part. Now we need to do it for a driven system. We want to get a master equation for a driven system, because when I do control, I have a controller that's, in my case, a classical object that gives time dependent Hamiltonian, and I have my quantum system and I have the environment. So now I divided it into 3 parts, and the question is, can I derive a master equation for this case, which is what I need for control. And what we do here, I would say, is similar in spirit to what you did. We enlarge our system to be fully quantum. So I have 3 parts. This is my controller, this is my system, and this is the environment. So the assumption, let's say, you could say the assumption on the environment is the same. Our system is whatever, and the controller has to have coherence in it. As in, if you think about it, if this is time independent, in order to have something happen, if the controller doesn't have coherence, it won't work, because there's a conservation law on energy, but there's a conservation law on global coherence. Global coherence is conservative. If you assume there's conservation of energy, its counterpart, which is coherence, and the energy from me, is a conserved quantum. So what you do in a setup like that, I have coherence here, I transfer it here. So initially you could say I have no coherence here. Here I never have coherence, it's a path. But when I want to drive something, I move coherence from here. Okay, so you can say here's my Hamiltonian. I have a controller Hamiltonian, I have couplings of different types, and I want to get semi-group property, which means the map has this semi-group property. I can get, you can say the differential generator of this map. And here, if you want details here, this is another paper of Ronnie in quantum. And what you do, you lump all these things together, and now I'm back in where I started before. Here I have my system, the controller, and their interaction is one system, and I have, and this is, you can say that, and the rest is coupled to the environment. And what you do, you get out of this condition, go to the interaction representation, that these 2 propagators have to commute. This is a semi-classical propagator, has to commute in this case. And so it commutes with a total unitary, but if it commutes with a total unitary, you can show it also commutes with a dissipative unitary. So if you have, you can say, an external drive, what you need to do, and this is in the semi-classical limit, you get the eigenoperators of the time-dependent unitary. And these will constitute the jump operators that you need in the limit operator. So you can see there, it's again, going back, it comes from this time translation symmetry. What generates your time translation in your system is the free unitary evolution. This sets the time. And once it sets the time, the interaction with the environment has to have the same basis, and which already tells you what's the structure of your master. Okay, so I escaped a lot of the technical stuff. There's a lot of technical stuff, but eventually, after you do everything, you get a master equation, was explicitly time dependent because I have a driven system. Now, you know, these operators here, they're eigen operators of my unitary evolution, and they have, you could say, complex energies like that. This is the unitary part, and they constitute the operators that sit in the Lindblad equation. And you have here these kinetic coefficients here, which still have to be determined, and they're determined from detailed balance, because you need another condition. If I don't have to assume detailed balance, let's say I have two baths, so I don't have exactly detailed balance, then these coefficients will be something else. But the structure is set by strict energy conservation, and you have freedom on these kinetic coefficients.
Ronnie, let me interrupt you for a moment. So usually when you have this kind of time-dependent Markovian seemingly master equation, often you can model non-Markovian physics with these time dependencies. So would you say this becomes a non-Markovian equation in general?
You could, the difference is just this. The kinetic, because this structure comes from the symmetry. This part depends on the, you could say, Bath correlation functions. So this part can be negative, and this would be non-Markovian, but you could say the integral should be positive. So we studied, you could say, the non-Markovian problem, strict energy conservation. We have a paper with Nina Meyer. She was in Milan at the time, and it's an interesting paper. I never met her in person. It's only a Zoom. So I know her daughter. I know how her house looks, and they never. Yeah. Yeah.
But where does the non-adiabatic enter here? The non-adiabatic thing? Is it
Because it's driven, and we'll see that. The non-adiabaticity you'll see. Now, the important point is that the structure is the same. So if I take, for example, just the Jaynes-Cummings model, which is two parts, energy conservation, and I want the reduced description of, I don't know, the qubit, let's say, for example, I can get this structure. So now the coefficients will be crazy. We've done that. So the structure is okay, but these will go up and down and have singularities and whatever, because it describes a reduced description, which is something the bath is too small to really.
Right. So you can have information come back in from the back.
Yeah, so everything, you could say the reduced description has the same structure.
So the idea is you turn the optical block equations into this kind of equation.
Yeah.
You have swallowed the driving Hamiltonian and put it inside the dissipator.
Yeah.
Okay.
Okay, so now we have a structure and also a way to calculate this. For this, I have to assume something about the bath to calculate the kinetic coefficients. I need to know their correlation functions. And so now we have an equation we can do control. Now, to tell you the truth how this worked, when we were in Santa Barbara, we did a standard derivation of the master equation, which is called Davis construction, which is second order perturbation. And we got this. But then we thought, okay, what does it mean? So we went around and derived it in a different way. So you could say we have the connection because you could get it either from a collision model or from second order perturbation. And this is a derivation. But when you do a derivation, you do approximations. But now I showed you an axiomatic approach. If I use these assumptions, I get the same. So now my job is to play with it. Okay, so most simple thing is a driven qubit. So, and I think this audience is good, so we think about it, but you'll see it's a little bit twisted to what you're used to. So here's my Hamiltonian. So I'm driving, I didn't write sigma, I wrote S, but SU algebra, so you can generalize it. But so I'm driving both this and this. Now I I need operators. We're in the operator world, not so we need an operator basis. So we know qubit has 4 operators that we can use, but we can use any of them if they're orthogonal. We don't have to use even orthogonal, but we need independent. So what we choose is our operator basis is time-dependent operators. And the reason to do that, we want to solve analytically the free dynamics. Otherwise, we don't get the eigenoperator. So I'm using this set. So the first one is the energy itself, this one. This one we call the Lagrangian, and this is a correlator. So here L, you can see, is kind of just has a minus here and a reflection. I switch omega and epsilon around. So you can check this is orthogonal to H. And C is basically sigma y or sy, the direction I didn't choose. Now, here's the Rabi frequency, which is what you have. And what we assume, and then I'll relax it a little bit, inertial solution. What does inertial solution mean? This is the adiabatic parameter in the problem. And this is to answer your question, if it's adiabatic or not. So if mu is 0, this is adiabatic, or close to very small. But mu can be very large. But the first assumption that we do is mu changes slowly. So you can say our slow parameter is mu. So this is, you could say that if you translate it to something, it means the acceleration is slow, not the velocity is slow, the acceleration is. Yeah. That's what we call it inertial solution. And you can show that under these conditions, if mu is constant, I can solve these equations, the free dynamics. Here they are. So I can write Heisenberg equations of motion. This is what I need. So I move the Rabi frequency out here. So this redefines my time. And I get a constant matrix plus, you consider the scaling with the identity. So this is analytic. I can diagonalize that. I can get the unitary, the free dynamics as a product of U1 and U2. U1 is just a scale of energy. U2 is mixing everything. Here, this is U2, and S and C and S are sines and cosines. And you can see that I get a new parameter kappa, which is 1 over mu squared. So if mu is 0, then kappa is 1. And you can see that the sine and cosine are modified by this kappa. So I get, you can say, an effective frequency here, and you can see theta is accumulated Rabi phase. So if I try to think what is the solution, why is it different than what we are used to? It's different that you have mixing of everything, so it's non-adiabatic. If it's adiabatic, we should get identity everywhere except the first one, because it should be in the energy shell. So that's why I choose these coordinates, so you can read immediately if it's not. So if I generated L and C, it's non-adiabatic. So if you see a matrix like that that mixes everything, it's non-adiabatic. Now you can see that the frequency is modified by kappa. So the accumulated phase is larger because mu square is larger. So I accumulate more phase by driving than I will do without driving. So there's 2 modifications to you can say this inertial solution. Okay, so what you see that I can diagonalize it and solve it. And we can get here the eigenoperators of the master equation. So there are 3 eigenoperators of the master equation. One is an invariant, which is like conservation of energy or something. But it's not only energy, it has the correlator built in. So this, you can say the it's an eigenoperator with 0 eigenvalue for the unitary. So it's an invariant of the unitary. So this is the if you think the Hamiltonian is the invariant of free dynamics if it's not driven. So this is the same thing just for a driven system. In this case, in this driving, and you can see mu, if mu 0 goes back. And then I have the jump operators, sigma plus minus. So this is plus. So I have here a minus, and here it's this imaginary part. And I get these operators here. And here are the eigenvalues. One is 0, and you can see the three. One is positive, one is negative, and you can see that. And here's again kappa, which I showed you before. No, I went the other way. What happened?
That's right.
No, it's the right way. No, so just that got me mixed. Okay, so just to summarize here, the two eigenoperators, here's kappa, here's the master equation that we have. We have k up and k down. This is a detailed balance. And you see it's with a modified frequency. So the detailed balance is not with a free, it's modified by this kappa. So when I drive a qubit, it effectively has a larger frequency. This is what we said. So this is the effective frequency, and here's the detailed balance as we had there. Okay, so now we have a master equation, we can play with it. And okay, so this is just to find what's called the attractor. So the attractor is time dependent. So we can calculate here, this is the entropy production, and this we can look at it like force, thermodynamic forces. We can write something that would look like Onsager relation between flux and force for this equation here. It's written like that. And what do you expect is what you get. If you drive faster, the entropy production is big. So this is reassuring because this is what you expect. If you do it diabatically, the entropy production will be zero.
Can you remember what alpha is again? I forgot what alpha is.
Where?
Alpha t in the first equation.
Yeah, that's the, okay, so now I relax, alpha was 1 plus kappa squared.
Ah,
But now I can relax this a little bit, like you do a diabatic solution, I can change it slowly. So that's why alpha can also become time dependent. When I'll do control, I won't keep mu constant. I can change it. Okay. So this is again quantum control of open system. Going back now, we have an equation, we can use it. So there are three issues about quantum control in general. One is controllability. The other, and for open systems, this is an open problem. It's not known. Constructive mechanisms, this I'll show you a few constructive mechanisms. So these are things that help our intuition. We know how this works. This is good to know. And then finally, I'll show you optimal control strategies, which are numerical, which gives us the optimal solutions. The disadvantage of optimal control, you get a solution, not always you understand. So this is why you need the constructive ideas. Okay, so this is, I would say, where we started, state-to-state control. I think this was brought by Ugolina and Santa Barbara as you can say, as a challenge for us to do so. This is the first thing we did. And the idea here is shortcut to equilibrium. I have an initial state, thermal state, and I change my Hamiltonian. And I want to reach equilibrium with a final state, with a final Hamiltonian at the same temperature. So I'm not changing temperature, I'm connected to a bath, so it's non-unitary. So I want to go from here to there as fast as possible with good fidelity or perfect fidelity if you want. So this is, you can say, the protocol. I'm changing my Hamiltonian from initial to the final and want to see how I get. So what would be the standard if you want to do that? A quench. This is what is known. What is a quench? I immediately go to my final Hamiltonian and wait. And wait until equilibrium happens. Now, before I go to it, if you think about it, that's a bad solution. Initially, it goes very fast because I'm far from equilibrium. But if I want to equilibrate, the rate of equilibration is a distance from equilibrium. So initially I go fast, then I'm crawling on my solution. Okay, this we did for, in this case, a harmonic oscillator, the standard things that you would do. Here's, again, the master equation looks the same, just everything here is time dependent. We used an algebraic setup to solve this. So this is again technical. And we could write equations of motions for the parameters that appear in the density operator. In a way, this parameter here, an effective temperature, if you want to think about it like that. So we can write equations of motion like that and try to solve them for a control protocol. This is what we did. So this is how you kind of engineer, I'll summarize this. Here's my state, which we write it as a general, it's a squeezed, you can say, if you look at this, this is a squeezed thermal state. And you can write equations of motion for the parameters that come from the master equation, beta and gamma. We assumed there's no squeezing in this case, but we could. And then if I get an equation like that, we have initial and final conditions that I have to obey. We used a polynomial approximation like that, fifth order polynomial with a reduced time. Out of this, we get a protocol. You can say beta as a function of time. We invert it to get alpha as a function of time. And you can say we invert it, and out of that we can get omega as a function of time, and that's the driving frequency. So here we start from here, we get beta, from beta we get alpha, from alpha we get omega, and we get the control.
So are you taking the equation of motion for temperature?
It's not, it's, you could say it's I don't like to call this temperature because they don't have omega here. So this wouldn't be
Okay, so
okay, I was Alexei here. It's a maximum entropy solution subject to constraints. So this would give you, you could say the constraint here would be the number operator. So this is, you could say is the Lagrange multiplier, which would be associated with this maximum entropy solution. So this is the structure. So what you did, you changed some density operators, you parameterized it in a certain way, and then you can solve it. You can give an interpretation to these parameters as Lagrange multipliers. Okay, now this is what we found. And these, you can say, this is a protocol here for expansion. So I go from frequency 2 to frequency 1. So I'm going down in frequency. This is what you need in a heat engine, for example. So that's why we studied this. This is a quench protocol. You jump immediately to here and then you stay constant. This is the diabatic protocol, how it would look. It would take infinite amount of time. And the red is the protocol we found. So we undershoot if you see this solution. Now this is for compression. We overshoot. So we go to a lower frequency, then go back. And in this case, we go to a much higher frequency and go down. What does this do? Here now we have a mechanism. Now we can look at the three variables HLC, as I said. This is the energy. If it would be a diabatic, I would stay in the energy. I would go from this point to this point. Now, this is non-adiabatic, so I generate coherence. So everything you see outside the energy shell is coherence. So what do you see, for example, that I generate quite a lot of coherence. So I start here at high frequency, at high energy, and I go to lower energy. So I go like that, I go down here, and then I go back. The same thing when I'm talking about the compression. I go generate a lot of coherence and go back. Now, how does it work? This is my pen by this, what the solution. The idea is I want to stay far away from equilibrium as much as possible. If I generate coherence, I'm away from equilibrium by definition. In equilibrium. So what can you do? You could change population to coherence. That's non-adiabatic. Now I have fast dissipation because I'm out of equilibrium. And when I'm happy with the amount of entropy I generated to change, I change back coherence to population. So you can say started on the energy shell, I ended on the energy shell, and in the middle, I generated a lot of coherence. So this is the solutions that we found. You can say and I think this is quite a general idea if you want to speed up equilibrium. Okay, so these are things, once we know how to do it, you can do all kinds of transformations under this thing. And this is what we would call constructive approach to control. And you can say what they said, the free dynamics is solved by the inertial approximation. So this type of solution is limited by the acceleration. And we saw the significant coherence is generated, and non-adiabatic drive mixes energy and coherence. And we found this mechanism, which is pen life. Okay. So now I've reached my optimal control. And now we kind of free ourselves. How can we free ourselves of adiabatic solutions? We have to do it numerically. So now we have to set up the equation. Here's the control equation. This is the same idea. And we want to do state-to-state control or process control, as I said before. This is, as we talked about that. Okay, so now I'm using optimal control theory. So how is it done? Now you see I need a double solution. I have to first solve the free dynamics, and then I have to get the dissipator out. So this is the algorithm. You guess a control field, something that you think. If you guess a control field, I can solve the free dynamics numerically. Once I solve the free dynamics, I can calculate its eigenoperators at each moment. So I get the Lindblad jump operator. So out of that, I can construct my master equation. I can calculate the evolution, and I could evaluate it. If I do final state, I can evaluate the objective. This is how you do control. And then I can optimize towards the objective. So once you evaluated the objective, you upgrade, you could say the functional derivative of the objective gives you the update to the field, and then you do this in the loop. So I can show this like that here. You guess a control field E of t, you calculate the free dynamics U, you get L, you get rho out of it, you solve the dissipative evolution, you evaluate the control objective, you update the field, you close the loop, and you do this until convergence. So it's not trivial, it takes time and patience, but we know how to do it, and I'll show you a few, I think for me, were surprising results. Yeah, so here, this is solving the free dynamics. You always can solve the evolution equation. And once you do that, you can calculate, and this is for small u, for wave functions, you can get the eigenvalues, and the eigenvalues, you can build the eigenoperators, and you get the Bohr frequencies. This is how this is done. And here are some solutions. So what can you do? This is state-to-state control. And in this case, it's a qubit, and we want to use the same setting for heating and cooling. And what we used is, in general, so we could scale up to not only to qubits. This is a Hamiltonian we used, which is I think it's called Bose-Hubbard. SU2, it's non-linear because it has UC squared. Now, what's nice about this Hamiltonian, it's completely controlled. So that's why we chose it. So we know that this would be our limitation.
And you check with repeated commutators and it's controlled.
Yeah, you could do that. You can do. So this, okay. So, and we're driving, you see, JZ in the Z direction. So you can make it a qubit or 4-level system or n-level system. So the idea is we want to study the same control problem in different dimensions. So this is just for a qubit, which is easy to do. So our objective is either to increase or decrease entropy. So on the Bloch sphere, here's I started. I started at this point, and you can see this inner sphere. So I'm a mixed state, not completely mixed, I'm somehow mixed. So I'm here. So you could say I can choose an objective to reach the origin. What is the origin? The completely mixed state. So that's a complete eraser of everything. Or I can choose my objective to be here on the X direction. And these are the solutions we found. So this solution looks straightforward. I go directly to this point. The other solutions looks a little bit strange. You kind of wander around and you almost reach the surface and then you go to the origin. And this is typical field. This would be epsilon of t. If you look at that, you don't see. And if I look at the difference in field of state 1 or difference in you don't see much about it. And you can see this is the entropy going down, or the difference between, let's say this would be the origin. So it's a difference in entropy from the initial state. So you can see it's not always completely monotonic, but it goes down. This is why we see this funny trajectory that we see. So this is, you can see, just shows you control works. It doesn't mean you completely understand it.
Are you looking for optimal solution or?
This is optimal control. So
Is it, so that.
So there are a lot of, what it means in order, it's numerical, but you can see that the number of iterations is a few thousand to get this.
So that was my next question. How come this only cost?
Yeah, so I don't want to dwell on this now, but if you're asking, you could say there are two basic methods to solve quantum control. One, which we used in this case, but then I'll show you another, is only initial and final information. And this is more catering towards experiment. An experiment, you can't look at the system while you're driving because it's quantum. So if you only take the initial and final state, you can, one way you can parameterize your driving field, and you generate what's called a simplex or structure, and you use standard derivation methods of optimization, typically conjugate gradient or something like that to find your solution. The difficulty with that you can't use a large space. These methods are MP, so you could use 20, 30 parameters. Another method is stochastic, which we didn't use here. And the other class of methods that you have access, like in a computation, to intermediate states. So specifically, we use a method that's called Kosloff, which is a great second order method that allows you to look at the system while it evolves. And that converges faster, but it's not experimentally dependent. So, okay, so now this I think is a little bit more involved. Now I want to do a gate. So this is a reset gate for a qubit. It's a 4x4 matrix because it's Lagrange space. And here's a Hadamard gate in Lagrange space. So this is completely non-unitary. This is unitary. So we started with this. Okay, let's say do a reset gate, and
you were setting to what, to the zero state?
no, to one of if this goes to sigma x, sigma y.
Sigma Y is.
Yeah, to projection, the projection on sigma. Pure state. This reset, but still it's a change in entropy. I don't know where. It's independent of my initial state. No matter what you give me, I end on the projection on sigma or minus projection.
Yeah.
Hadamard, so this is Hadamard is a unitary. And we have an open system, so it's non-unitary. So we ask ourselves, can we do a unitary in this case? So this is Hadamard. In this case, okay, I choose one example. I started in sigma x, I ended in this case minus sigma z. So this is what you should do. Now, we did three things here. One, we solved the control problem of the unitary, and we found a certain solution, which is this purple line. You see, it goes this loop and goes back here. So this, if you look at it, it's just one. There are many solutions for a unitary. So this is a solution that we find, and its fidelity is, I don't know, 5 digits, 6 digits. Now, if you look at this purple one, it's all the time on the surface of the Bloch field. It doesn't lose purity. Now, the yellow one, we took this solution, just added our path, our dissipation. So you see we're going everywhere and ending up here. So we ended on the green, so we lost purity, and quite a lot. If you can see it, it's a lot. Because the threshold law says 10 to the minus 3, so you wouldn't see it on this plot. And we end nowhere. I don't know, we started in California and we ended in Alaska instead of in South Africa. So then we said, okay, now let's fight this dissipation and use optimal control theory and ask, can it find a solution that will lead us to the right place? And this is this blue solution. You see, it's simpler and it ends here. So what we found that we can do a unitary gate under non-unitary evolution. So we, in a way, our control was able to fight the dissipation. Now, you could ask here, and this shows, this is the objective. So you see, eventually, here we reach the objective, and if we just, this is how far we are from the objective, if we just use the same, the unitary solution was a dissipation. And this is the log, just to look at this piece here. So we see, this is the unitary, so it's, okay, 8 digits we could get. And with the bath, we could get about 3. So if we would get perfect, it would be wrong. I know we have to, dissipation has to be, so this is, you can say the field doesn't look too difficult, but I would say this is the interesting point about. When people try to find gates under dissipative conditions, which everybody as a quantum computer does, there are all kinds of tricks, which is dynamical decoupling, there's decoherent free subspace. Is this part of this class? The answer is no. This is thermodynamics. The entropy production is huge. It's not, if it would be decoherent free subspace, entropy production should be 0. It's huge. It's very far from equilibrium. I'm pumping a lot of energy into the system. It's dissipated to the bath, but it keeps my system quiet. So it's a refrigerator, but a generalized refrigerator. I'm using power to basically keep my system quiet. So we can say here, this is orders of magnitude. Entropy relative to the system entropy is huge. I think it's 2 or 3 orders of magnitude. So we're really dissipating a lot. Now, here we could do a 2-qubit gate, because if you do 1-qubit gate, you did nothing. So we could do a 2-qubit gate. And this, just to make it universal, we took a square of a swap. So this gate. So this is not in Lagrange space. This is 16 operators. 2 qubits is 16. So I show it in like that, and was as this tensor product to show you this thing. It works in the same way. Here you can see that we get a good solution for a 2-qubit gate. It's more expensive for us to do, but we can do that. So if I just pause here a minute, what we found out that we can fight, either it can exploit the bath or it can fight it with the same control. Our control is only on the Hamiltonian. We don't do engineering of the bath. The bath is always the same. Okay, now let's look at something a little bit different. And this noise originating from the control. And this, if you're an experimentalist, you know that one source of noise is your controller, your pulse generator. And it's you can't really avoid this noise. If you do nothing, it's quiet. This is our assumption. So this is something that we analyzed, I think, 10 years ago in different contexts. And so we knew something about it. So we said, okay, can we fight this type of noise? And to generalize, there are two types of noise in the controller. One is amplitude. So let's say this would be my control field. And amplitude means that I miss. I don't hit the right one. The other noise that I don't update my field at the right time. So you can say if I discretize time, so I don't do it like you did very precisely, I add random noise to my time. So you can show that this case leads to this type of master equation, but it depends on the control. And this case leads to a double commutator with the Hamiltonian itself, but our Hamiltonian is time dependent. So these are now the fidelity of these two cases. We have analyzed this case, the first case. The fidelity can be shown that it's related to the variance of the control operator. So you already know if you want to fight that, you want to reduce in your system the variance of the control operator. Now in this case, there is this expression, there's a archive paper that came out with this expression for timing noise from Marcus Haber, who came up with this expression. But we ask another question, can we fight it? So here's example of phase noise, just to show you. So I want to do, again, this is a Hadamard gate. So I want to reach here to this pole here. So this is a unitary, the yellow. And if I add noise, this is phase noise, you can see this is the loss of fidelity. So I go inside. Now, if with control, here the blue, you almost don't see the difference between. So it means I can fight phase noise by proper choice of my control field. You can do that. So this is recent results of Aviva Hoch. We haven't published this yet. We're writing this up basically. Okay, so I think I gave you, I hope, an overview of control of open systems. And take-home lesson, the dissipative unitary generators are late. And why do I say that? If you go to IBM and you see what the engineers do there, they simulate their experiment or their computer, I wouldn't call it, with Lindblad equations. But their dissipator is independent of the draft. And that's, so this is not correct. They have to be linked. So either they linked in one way through the thermal bath, or they're linked because the noise comes from the controller. They also have to be. And you could say the dissipative generators comes from the free dynamics. And this is how you do the control. You control the free dynamics, but indirectly you modify the dissipation. And that's how you get entropy changing transformations. And what I showed you, two types of things that we could identify. One is this Mapemba effect. And the other is what I call tracking. You active cooling while performing your unitary test. So you all the time try to keep in a way your system cold while you're changing. So it's active cooling. And with this, here, there are two papers that we published. This is a recent paper here with Roidan and Shimshon, and which describes controlling these gates. Here we published that. And this is a general, I would say, Christiana Koch was the initiator, but you can see many authors on this review paper, which tells you about quantum optimal control in quantum technology. So this is a review, I think, that came out a few months ago or something. So if you want a big list of people who are working on this subject, you can read this paper. And I think I'll stop here, but I really want to stop here. Questions, please.
About the shortcut to equilibration.
Yeah.
So I suppose one of the reasons to do that is that if you can shorten the amount of time it takes to thermalize, you can increase the power of thermal cycles.
Yeah, this is one motivation.
Yeah. But so my question is, but how much energy you use to make this shortcut to equilibration? So in the end, do you really increase the power or not?
Okay, so your question is very good. Because you're right. If you want to speed up things, I go away from equilibrium and I'm going to have more entropy production, which will cost me with the drive. I need stronger drives to do that. Now, so what you get is what you, in a way, expect in a field called finite time thermodynamics. There's a trade-off between, you can say, speed and power, or efficiency and power. So what happens if you want to drive it faster, you pay with efficiency because part of your power goes to speeding things up. So it's an optimum. So if you look at, you can say the curve. If I look at an engine, we did that for different engines. So this would be the cycle time, and this would be the power. So here you're at the adaptive. So up to a certain point, it helps you. And then it costs you more to drive the system than you get power out of it. So from here, it's useless. So there's an optimum. So if you do, let's say, for example, Carnot engine, you would get it here in a different cycle, auto cycle. You could get to shorter cycle times with less power. But this effect comes from two things. One, equilibration. You want to speed up the equilibration. So this is one effect. And then the adiabatic move you can do better. You can avoid. Yeah. So this is universal. So your intuition is right. It costs you. There's an optimum. Then forget about your engines.
Can I bounce back on the question? So here what you do is to set up a framework where it's kind of analytically or numerically easier to reach the solutions where you go faster to equilibrium.
Yeah.
Yeah. And can we use the same framework to minimize the energy cost to reach a certain fidelity?
To minimize, yeah, you could, okay, so you could say.
You pick the fidelity of your Hadamard gate, for instance, and you minimize the work cost.
You could do that. Okay, in a way we do that. Because, okay, yeah. Okay, when you do optimal control, so you define an objective. So the objective, let's say here, we'd say, okay, entropy, the final state, or the objective could be the fidelity. This would be, but that's not sufficient. That's why we saw many solutions for the unitary. So typically you add another constraint on power. So I would say, without thinking about it, we optimize power. minimize power. And you could say the reason is partly numerical. If you don't regularize your solution, you don't find it. But also you could say it's physical. You want to find a solution that's minimizing the power. So this is very typical. Almost all what we do, we have a constraint on power. So if you see a solution like that, we minimize power.
Okay. So then I have another question. The situation from which you start is a situation where your system is already living in a like pure environment, in the sense it's just a little bit of noise that comes and perturbs the system. I'm going to my question is, that was not the cost of preparing this quantum system, which is already sorry, actually in the mindset of tonight, because this is very connected to the cost of quantum technologies, where basically you never really take into account the cost of building the classical context around your quantum gate or around.
This I also don't do, but on the other hand, let's say I do a reset gate. This is the first step in any quantum computer, is a reset.
The first step is to have the cryostat or
Yeah.
something like this before going to the reset. So no, but I was just wondering if there would ways to like adapt your framework and your methodologies to this more complex situation, or if it also goes with this idea of having a complete description of the world and this as long as you have not solved the measurement postulate, we cannot really model things like this. What would be your intuition?
Okay, so it's an embedding problem. You want to increase your system,
Yeah.
and in a way, I would like to treat my controller as a quantum system, and we could do that. But
Yeah.
then my optimization would be on the initial coherence.
Yeah.
Right? So you could twist that, and that would be more aesthetic. But what is the price? The price is my Hilbert spaces increase. And
Yeah.
that's my budget. My numerical budget is Hilbert space.
Mhm.
So this I could do. Like a simple controller I could do, but once you could say you increase your Hilbert space,
Yeah.
it now control. There's a point about control. When I do quantum simulation, that's solve the time-dependent Schrödinger equation. So it scales semi-linearly with Hilbert space. So Hilbert space grows, it's that, but it's semi-linear the methods. But when I do a control, so we found out when we do a control on a gate, it's MP. It scales with the size of the, let's say factorially difficult with the size of the control we want to do for a gate. And you can understand why, because what you're doing, when a gate is independent of initial conditions. When I do state to state, I find the solution. But I have n state to states in a n by n matrix, so they have to be orthogonal to each other. All solutions, it has to work on one and not the other, so that's why it's factorially difficult. But otherwise, you would think that I could solve on a classical computer
Yeah.
an empty problem. So
It's about
when you're
quantum computer.
yeah, but you could say like 1, 2 cubic gates. We went up to 32, not 32 by 32, so it's 5 cubits. Practically. Yeah.
I just wanted to know, when you do this process to optimize the control, you say I do this thing up to the end line, I see how it performs, and then I change the control and I go back and I will do this same thing until it converges.
Yeah.
And you say this is optimal, but I was thinking, could you just be stuck in a local minimum of your parameters?
No.
No.
The answer is no, but that's not trivial. There are studies that show what is you could say the landscape.
Okay.
So it's not always correct, but if you don't constrain anything, the landscape is flat at the top and monotonic.
Okay.
So it means you have like a mesa. Forever you go up and you reach the top. What does it mean that the top is flat? That there are many solutions. So this is a general topology of the problem of quantum control. Now, if you put constraints, you ruin this topology. So if you put too many constraints, you could be stuck in a local minimum. Okay. But the way we work around it, if you put an external constraint, you change it. So we find, let's say we find that it looks as if the solution is stuck. So let's say my constraint is like Alexei wants on the energy. So it's a Lagrange multiplier. So instead of being 5, I put 6. And that frees you because it's the general problem has no local minimum. It has saddle points. So there's, you could say, a series of paper of Rabitz and people who worked with them on that, which is based on an idea of von Neumann, that you can prove that, the topology of these problems. Okay.
So I wanted to ask more about this Mubaba factor. How do you say that?
Mapimba.
The Mapimba. So I've known about this fact for many years now. I don't think I knew it by that name. But I just want to understand it better. So can you tell us how it works and you hinted at something that has to do with like the acceleration of the state there.
Okay, so I could give you a simple mathematical. So I take, let's say I have a master equation, and I have its, so I diagonalize it, and I find its eigenvalues and eigenoperators, my master equation. But now I look at the eigenvalue. Now in the master equation, you know they decay exponentially. So the largest eigenvalue will decay fastest, and the smallest eigenvalue will decay slowest. So if you want to accelerate your integration, you want to avoid the last smallest eigenvalue.
That's the one you typically go to.
Yeah. So what you do, if you have control, get rid of it.
I see.
In a way, this is what we're doing. So you control and you move this, you could say the populations at this one to a higher population, and you relax fast.
Mm-hmm.
So this is a general, you could say, strategy that always should work if you have the ability to control. But in quantum mechanics, we have something that you don't have in classical mechanics. We can go to another dimension, to coherence. And we always know this is going to be far away from equilibrium. And we have a method to go from population to coherence and back. So this is what we can, so that's why it always will work better in quantum mechanics than in classical.
And what if I return to ice? How does it work in ice?
Nobody knows. I have a guess. You see, when you heat up, you reduce the density. So the question, when you go from water to ice, there are two things that happen. The temperature changes, but the density changes.
Right.
So if the constraint is density, it's better to go high. Maybe.
Because you expand when you freeze.
Yeah. Yeah, you're
Yeah. So the Euclidean mass equation usually describe the dynamics that is dissipative, right?
Yeah.
And I was wondering that whether there is a general scheme that you can control quantum state to remain its current purity or even increase its purity under noise.
I showed you an increase in purity.
But
what I showed you. If I have a bath, the reason I could do that because I'm not violating thermodynamics. Here, I'm increasing purity. I'm both decreasing and increasing in the same control setup. Why can I do that? Because what does the refrigerator do? It pumps, you can say, entropy from your, I don't know, whatever you put there in your refrigerator, let's say, I don't know, milk, and pours it into the environment. This is what I'm doing here. Why can't I purify it? I'm taking the entropy out of my qubit and throwing it away into the environment. Why can I do that? Because it's an open quantum system. If you want to think a little bit more how it works, I'm now inventing really a mechanism. You could think about it like that. If I drive it, I can make a very high effective frequency of my qubit. So now, if I equilibrate with the bath with a very high frequency, the population, it will be very pure, right? Because the frequency is high, so I have most of the populations in the ground state, so I purified that. So this is one way. And if I want to go to the origin, I'll do the opposite. I'll make effective frequency that's very low. It's an effective frequency. You don't see that when you write it like that, but this is what you can do. You can basically, in a unitary way, change the natural frequencies of your problem. So if you could say in general, if you want to cool, go to high frequencies. Your bath is constant temperature. And if you want to do the opposite, make it a general.
You're not always playing with thermal bath here, are you?
In this case, it's always the same bath. It's
Yeah.
always thermal.
Yeah.
And it's not zero.
Okay.
Now, there's a third law here. I can't really, if you look at it, I really can't reach.
But in your formalism, it's bath agnostic. You could do your magic for any kind of bath, or it has to be thermal.
Okay, in this work, it has to be thermal. No,
Not-
but in the other
general.
case, it's noise bath.
It's noise bath, yeah.
I can do
So
also
can-
noise. So what
yeah,
I showed
okay.
you here later. This is noise bath.
Okay,
So I can do the noise bath. You could say noise bath is a good question. What is it? Is it heat or work? So it carries no entropy. I say it's work. So this is a noise bath.
So you say that you have to know your state, right? When you do this optimizing protocol. Do you also do the like black box type of optimization when you don't know the state or?
No, so this is a gate. A gate, you optimize the gate, not the state.
Okay,
The way you optimize the gate, you need a full basis function of operators, and you know this goes to here, and you do them simultaneously. That's why it's much more difficult to do a gate. So that's in a qubit gate. I have three operators. I have, let's say, I want to bring x to minus z and y to this and this to this. So you find a control that simultaneously achieves the control objective for each possible state in the full palette of operators. Okay. So
so is
this
that
is the difference between, you can say, state to
gate option?
to gate optimization. This is why it's so different.
Question. I might not be completely correct here, but so in your method, you have essentially, if in the Lindblad equation, you have combined the commutator part into the dissipator and written a master equation, right?
Yeah.
Now, but this reminds me of the other case where people work with non-Hermitian solution, where they write the master equation rather as a commutator with a non-Hermitian Hamilton.
It's not the same.
Yeah, I wanted to know like where.
Okay, so you could. You could say like that. Formally, if I write it, look at my Liouville equation, it's non-Hermitian, and I can apply the mathematics of non-Hermitian quantum mechanics or non-Hermitian operators. So this is now, but you could say there's a strong constraint of completely positive map. That means that my equations conserve identity, if you want. I'm not leaking out of my system. Now, when I write typically a non-Hermitian quantum mechanics, it's typically for scattering. This is where it was born. In scattering, you go to infinity. You don't care if you lose your population. So you're, once you make a Hamiltonian non-Hermitian, it's not unitary.
Well, not sure.
Or you basically say you go conserve.
Yeah.
Yeah.
I just didn't know.
So there are differences, and so you could see the mathematics is similar, but it's not the same. Now, you could say that this raises the question: can I find exceptional points here? This is for you, and in this construction, I think not. This Lindblad equation won't have exceptional points because if it has the same eigenoperators as the free dynamics, they could be degenerate, But to find non-Hermitian degeneracy, I think not. Not in this case. If with noise, yes, but with this, no.
Yeah, please.
Well, yeah, I'm out of time, but we don't care.
I'm not, I don't care. This is, it's more
Don't care.
important that we talk than I
Okay.
think to a schedule.
Okay, yeah, I want to come back on the energy restrictions.
Strict energy
Yeah.
conservation.
Strict energy conservation. And so that's the criterion that you take to have a thermodynamically consistent
Master.
master equation. So can you elaborate a bit on that, in the sense that what I saw before in the literature about getting something that is thermodynamically consistent is that we extract some heat and we check that it's consistent with the second law.
Yeah.
So here it's not like this. It's
It
just-
is consistent with the circuit.
I'm sure, but it's just that you changed the condition, and now you say it's because we want something, you look at the energy flows basically. So how is this connected with the, I would say, the condition I'm used to, basically?
So this is the condition. So this is the condition that you. So there's a long history of master equations
Yeah.
from Lindblad. And you could say in parallel, there's Davis, which did a derivation. So before Davis, or before I think the first master equation is Schwinger and Kauplus, 1946. So Kauplus, not the Kauplus we know, this brother was a professor of physics. He did his PhD with Schwinger, and they wrote a collision model. So this, if you want, the first reference for a collision model is there. Now, in a pure collision, you obey this restriction automatically because the S matrix commutes with the total commute. So collision, this works. You don't have to say anything because of the trouble about collision model, you go from here to there and the particles separate. And so it's as a model, it's automatically it obeys that.
Mm.
Now, the perturbation expansion, when you do, which starts with, Bloch did it, and it's called Redfield equation because Redfield worked with Bloch, and Bloch had too many equations on his name, so we call it Redfield equation. So that's a second order perturbation. Fano, there's a very nice paper, Fano, which treats that, and Fano already started to check about consistency with thermodynamics. And you would say you would want the fixed point to be a thermal state, for example, or something. And that you could say there was no interest after GKLS equation came out in Davis. And then there, I think the first kind of mention of that is in a paper of Leibovich and Swan and Leibovich. Same Swan inequality. And Swan and Leibovich, they have this condition in a different way. In their case, it's a secular approximation in the derivation, but the secular approximation leads to this condition. So the question, what you assume. So they did a perturbation, and on top of that said, put a secular approximation. What does a secular approximation says? If I take something from here, I put it there. This is a secular approximation. So rotating wave.
On the same thing, your number one, can it be restated as I have a system and I weakly coupled to a thermal bath and I forget the initial statistics?
What, number one?
Yes, then it is Markovian, right? No matter what.
Yeah, but you could say, okay, so you want the map to be Markovian, and you don't have to have that, but that's an assumption. But when I say the statement, I don't need a bath. Just to say, Markovian I can get from noise. Noise is also Markovian. So you say one is that's why it's an independent statement, and I don't have to say I'm weakly coupled. Okay, that's in a collision model. You're not weakly coupled. The difference in a collision model, that the events are rare, so you don't have collision between events. So each event can be very strong, comes and goes, and I think we had a nice example of that. Yeah.
About the last type of business, I mean, you could just, I mean, you could leave it
and you would, I mean, the model would still work, but it,
Well, if I release this,
yes.
I could replace it with another symmetry. We tried that.
But, I mean, do you need to replace it by something? Could you not just remove?
Okay,
it?
if I remove that, okay, if I remove these two things, I get Lindbergh.
What?
I get just Lindbergh equation. If I remove 3 and 4, I get Lindbergh.
But then you have anti-thermodynamic behavior.
Yeah, but then it's not thermodynamic. I can get heat going from cold to hot.
And if you remove just the last one, I mean,
Okay, you could say there would be an argument. Asymptotically, the last one is correct. You can't remove it. But you could say temporarily at short times, maybe this is too strict. Because you could say short times anyway, my energy conservation is not, energy is not well defined at very short times. So you would want to reduce make this less strict in short times and make it stricter to long time. So there are papers, there's a paper of Alitsky about that and other people who replace this, you could say, strict energy conservation by kind of a sink function that becomes more like a delta function that leads to that when time progresses. So this would give you some leverage on your master equation, which I think is a good idea for instance, if you're interested in very short term.
but why do you even need it at long times? I mean,
Okay, what is long? Long is the bath correlation. That's a time scale that. So typically the bath is fast. This is a typical assumption that the bath is fast. So if the bath is very slow, then it would be something else. But you can say that that's the justification for Markovian.
I think if I may jump in, I think that what Leah is missing here is a little bit of context around this Lindblad that allows you to break the second law of thermodynamics. I know that you worked a lot on that, and if you just put in the same equation, the driving and without changing the dissipator, then you can have stuff that is completely irrelevant. So that's what actually is the context. And one solution is really to start again from a microscopic model and rederive the proper Lindblad equation where the dissipator gets modified, or going through this approach where it's actually embedded in the way you derive the master equation, and you don't have to fear that you will become that you will break the second law. You know.
So for example, in a driven system, if you take a qubit and drive it and have an independent dissipator and time-dependent Hamiltonian, what you can get that you can extract energy from your bath and make work out of that. That's a violation of the second law. So you can see that the field increases on there are certain conditions that you can see your equations is unstable. And the solution is you have, if you derive this master equation, which is you drive it, I do the free dynamics, and then I connect it, that guarantees the second law. The second law is automatically obeyed here.
Maybe I'll give one more question and stop. So one of the things that Lihu, my student, is working on is this issue of controllability, guiding states along particular paths, and particularly thinking about the mixed state case. And so in your example, you're dealing with open systems where you can use the environment to change the entropy of the system. And we're thinking about a situation that's sort of philosophically different. Imagine we have two parties, the Alice and the Bob, and Alice can apply, say, one of two unitary operators. She flips a coin, heads or tails, and she applies either U1 or U2. And from her point of view, everything remains pure. But from Bob's point of view, he doesn't see which operation is done. He has ignorance of the situation, and so he has to assign mixed states so you can change the purity. And we're thinking about guiding states in this kind of scenario. So how do you do that situation I just posed in terms of the approach you outlined here?
Okay, so what Alice does is I would call this, I think it's related because I would think this is called tracking. You have a trajectory of Alice that you want Bob to track.
Right, or you even want to be able to try to apply some kind of controls.
So who applies, Bob or Alice? I'll say, let's say Alice defines a unitary control.
Yeah.
And Bob wants to track that. That he is allowed to use extra controls. I would call that tracking, and you could say this formalism could work.
Okay. So even though there's no thermal baths involved, you still have the ability of changing.
The reason Bob does, there's noise or something, or what's missing in Bob's case.
Yeah, that he doesn't see which of the coin flips are applied.
Okay, if I could translate that to a master equation.
And you can, right? You can write simply a map that
Yeah,
now is
you
the
could-
coherent sum of the two unitary, weighted probabilities of
So
that.
if you can write, let's say, for control, you need an equation. This is my whole point of my talk. If
Yeah.
you can write an equation and
Yeah.
it's tracking, and you want to follow this, then it's a control problem,
Yeah.
and you can use this formulas.
Yeah, good. So I think this is helpful. Yeah. Okay, good. All right, let's thank Ronnie again for the. All right, so even though we're over time.